Everyone probably heard of Rapids now. We've been out promoting it for 4 years. Basically, you have cuDF, which is our data frame library. You can think of it like a accelerated pandas. cuML, which is accelerated scikit-learn. And what I'm going to talk about is cuGraph, which is very similar to NetworkX, just runs faster on GPUs. But Rapids also has a large collection of other libraries. Raft, which is kind of a general reusable accelerated function toolkit. It started really as a combination between the Graph and ML team on shared primitives that we both use. We figured we'd put it in a central place, but that's out there for people that want those type of primitives. cuSignal, cuSpatial, cross-filter, visualization. There's lots and lots of libraries out there. So the cuGraph stack, we love Python, but CUDA is written all in C, C++, and then we start adding very lightweight Python wrappers around it, and then more, robust Python layers on top of that. So at the top layer, we have cuGraph. It provides a lot of data translations, convenient functions. It makes the whole process easier for data scientists. The vision of cuGraph is to make graph analytics ubiquitous, meaning that as a data scientist, if you need to do graph analysis, it should not feel like you have to jump into another tool. It should just be seamless with what you're doing. Just like, you can bounce back and forth between pandas, NumPy, you pass all these objects, it feels the same. Years ago, if you wanted to do graph, you actually had to step out into a specialized graph package that was separate and on its own, but we want everything to feel seamless. Therefore, inside of cuGraph, there's lots of convenience functions. You can pass in, cuDF objects, pandas objects, SciPy, sparse arrays, NumPy objects. You can even give us NetworkX graphs. We'll run with all of those. So whatever you're doing, we try and provide an interface to accept it, run with it, and give you answers back in the same format that you gave us the data. So if you give us a NetworkX object, we'll give you a NetworkX-like answer. As you go down the stack, we come down to the C and C+ layer. A lot of the national labs don't like C++, so we had to give them a C layer. And then we have a closed source level at the bottom for GNNs. We are slowly working to open source that. It's just a slow process to go through all of our IP reviews and get permissions to open source it. So this just gives us a place to write something fast, put it out there, and then work through the process of getting it open sourced. We're also working on some other things. One of them is called Graph as a Service. This basically wrappers cuGraph and actually a lot of the graph ETL stuff in an RPC framework. This way you can have your graph running in a remote cluster and still access it, and it will feel like it's local to wherever you are. You can do it from a machine that doesn't have a GPU, and it just runs off in a GPU cluster somewhere. We're slowly rolling that out. It's out on Conda now. You can try it out, but just know that there's a lot missing from it. We have a large collection of algorithms, always adding more algorithms to it, always interested to hear what the community is interested in algorithms. It is an open source project, so sometimes if you say, hey, how come you don't have algorithm X? I'll be like, hey, you're willing to write that one for me? I will gladly integrate it. We're also moving to make sure all the algorithms scale. NMNG stands for multi-node, multi-GPU. So on a single GPU, roughly a 32 gig GPU, you can have about 500 million edges per GPU. We like to scale out to big problems. So we scale out to multiple GPUs in one box and then multiple nodes across multiple boxes with various type of interconnects. And the hope is that, I'd like every algorithm to scale for however big you want. And talking about scaling, we recently published some results on us scaling up to 1 trillion edges. PageRank at 1.1 trillion edges takes 19 seconds. For our team, that's still very slow. Did Louvain clustering, also on that same size. Takes a little over 5 minutes. I think we're trying to cut that down in half. These are old numbers because a week ago we ran on 4 trillion edges. So we are really trying to do big problems. If you think of like large retail stores that have, 1 billion customers and 10 billion products, the size of their graphs can get very large. And we like to try and give them solutions. So 1.1 trillion edges came out to roughly 20 terabytes of data. So bring us your big data. We'll throw it in there and we'll run graphs on it. This talk is really about doing graph analysis and not as much about the product, but I will discuss the product as we go. All of the code is in a Jupyter notebook. It can be found out on our Rapids community site in your GitHub. There's lots of notebooks for every conference we've been out for the past 4 years, plus lots of example notebooks. Within the cuGraph GitHub repo, there's also a notebook folder where we go into depth about every algorithm and then communities of algorithms we talk about. I'm not going to be running my notebook live. I've always run into problems with networks or something else that always concerns me. I also gave away my gaming laptop to a coworker, so I'm on a Mac without a GPU. It's a lot easier. I would say the downside is that I did find a bug in my code, so I'm going to kind of wave my hands past that little bit of the code as we go through it. All of this was run on my local workstation. It has an RTX A6000 in it. So not the fastest, but a good GPU. And I will show some comparisons against NetworkX. For those interested in social networking analysis, I have a little call out over here to INSNA, which is the International Network for Social Network Analysis, or analysts. This is really a group of social scientists. They're always not that keen on computer scientists, but if you'd like to really know how, sociologists apply this stuff, it's a great group. They do their own conferences. From the social science perspective, these people will get embedded with gangs, or they'll spend 6 months in some research facility, and then they'll talk about how people interact. And they will complain that what I'm doing is really graph analysis and not social network analysis. But I don't see any of them here, so I'll call it social network analysis. The data, I'm using a Twitter data set from this paper. Just like to say, I have no affiliation with it. This just seemed like a cool data set to use. Getting a data set is kind of always the toughest problem. So I'm using this data set. I'm not making any claims about what I find in the data set. It's just I'm exploring it. I always think Twitter is an odd data set because you can see interactions, but interactions don't really show social relationships. So, if some, movie star posts something and I like it, that doesn't mean we're friends. Doesn't mean any relationship, but it does show a connection somehow. So, cuGraph, easy. I import cuDF and I import cuGraph. This would be the same as importing pandas and NetworkX. Simply load the CSV file. I do some pretty printing there, so I can say, I got a little over 7 million records in this data set. Again, for cuGraph, that's what we call a small data set. Once you start thinking in the trillions, anything in the millions becomes small. And I can see that there's, 5 million retweets, a little over 1 million replies, 700,000 mentions. Or let's see, M is, mentions in a tweet. So using cuDF, this takes 148 milliseconds. Pandas, 6 seconds. Almost 7 seconds. So definitely a speed up as your size of your data grows. The delta between how fast cuDF works over pandas grows. The ability just to get data in there and analyze it, dive into your analysis rather than waiting for it to loading is something that team focuses heavily on. But syntactically, those are the calls are the same. And in this case, I'm not specifying anything about the structure of the rows. If you want to make it faster, you define your columns and the data types of the columns. So looking at this data, I have a from field, which is strings, to field, which is strings, the type, status IDs, and a width, none of that I'm using. Creating a graph is similar to how you do it in NetworkX. I say I'm going to create a graph. Directed is false, meaning that I want an undirected graph. I then add my edge data to it, specifying source and from, and then I can look at how much data is in there. cuGraph, we allow the source, well, the from and to be any data type. In this case, it's strings, but it can be anything. And under the covers, we convert it into a numerical sequence starting at 0 and being contiguous. Down at the CUDA level, everything is a matrix, so I need index values. We also support specifying the source and destination in multiple columns. So if you think like lat long data or geospatial information, first name, last name, we test up to 5 columns. The more columns that represent your source and destination, kind of the slower it gets, but we want to be as flexible as possible. Right now, we enforce that the from column and to column data types need to be the same, but we are thinking about changing that, especially when you start thinking about bipartite graphs, where one side can be users and the other side can be product IDs. So we may have multiple sets, and as long as your columns are, within that set of the same data type, we'll accept it. As I said, if you set directed to false, we symmetrize the graph, so that means we double the number of edges that are in there. We also have a new property graph coming out, so I could have taken all these other fields and added them to my graph, but I'm not going to get into that yet. Rick Ratzel has a poster, a virtual poster, so there's a PDF out there that you can read about where we're going with property graphs. But looking at this data, it looks very odd. If I divide, the number of edges by the number of nodes, it comes out to approximately 2, which means that every vertex only has, 2 edges on it. So either this is a giant straight line, or there's something else going on in the data. And the easiest way to figure this out is, well, I'm going to look at the degree. So I just call the degree function. Since this is symmetrized, the in degree and out degree will be the same, so don't worry about that part. And then I just call, the simple describe method. Send it to pandas just because I like to do some pretty printing here. So it shows that, 50% of the data only has a single edge. 75% only has 2 edges. So this indicates that it's really not one graph that I'm dealing with, but probably lots of small graphs. And the way I'm going to dive into answering that problem, well, just a quick note here that, when I'm doing my sorting, sorting is fast, so I don't always save the results of my sort. If it only takes 6 milliseconds to sort, I'll just be lazy and resort every time I need it. So weakly connected components is a great algorithm for finding disjoint subgraphs within your main cluster. Weakly connected components basically says if there is any type of path from one vertex to every other vertex, that forms a community. Well, not a community, but a cluster. So I run weakly connected components. It produces a nice output, which I did not print here. But it basically assigns a label to every vertex. And then every vertex with that same label is in the same community. So I just do a quick count. It tells me that it found 107,000 communities. So I know that there's a lot of communities that are really just 2 people talking to each other. So, I mean, if you look at my Twitter account, it's just me and my friend bantering back and forth. So, there's a handful of us and no one else gets involved in our chats. I guess I'm not that interesting. But then I go through and I count the number of labels, well, the instances of that label, come up with a count. So there is really one community of interest that has, 2.6 million nodes in it. And then there's all of these really small ones out there. I'm not going to worry about the small ones. I really care about the large community here. And to do that, I have to now I get the max ID. I convert that back into figuring out what the label is. I then go into my components, pull out every vertex that has that label, and then I use the subgraph extraction function. And that will go into the main graph, pull out all those vertices and all edges that are involved with those vertices. So I can now come up with a new graph that is just this large component. It still is pretty large with, average degree is small. And just for fun, I decided to throw it out there in the Gravistry to see what this thing looks like. If you have, 100,000 or more vertices, it's really no point in plotting it because you just get this big blob. But it's always fun to see what it looks like. Graphistry has this free interface out there that you can just register for, send your data to, and it will plot it, and you can interact with it. If I was connected to the network, I could move things around, introspect different things, but it's very tough to see, 2.5 million vertices out there. So let's talk about importance. The concept of centrality. Who is the most central object in there? And I'm just going to define this function here. It's going to call degree centrality. Degree centrality is basically saying, if you have a lot of connections, you must be important. Betweenness centrality, that's basically if more paths go through you than other people, you must be important as well. So it's the number of shortest paths that cross over that node. That's how we come up with that count. Betweenness centrality is a very expensive algorithm to compute. Basically, it's doing a shortest path on every single vertex. So we use this estimation technique. In this case, I'm going to use just 100 nodes and then estimate the rest. The estimation works great for nodes that are important. But if you are very low centrality score, it starts guessing those. But we usually don't care about the low centrality score ones. So the fact that those values are not correct really doesn't matter. The ranking is really what's important and comes up with a good ranking. Cat centrality. Cats came out way before all these other algorithms, and the paper sat unpublished for 10 years before they finally got around to publishing it. It is kind of like a hybrid between PageRank and eigenvalue centrality. And technically, if you sent the cat scores to certain parameters, you can get eigenvalue. And eigenvalue basically is a spectral approach that finds those nodes that are kind of central. Then I define just this pretty printing thing. I like everything in a nice table. I sort each of those values. And then, just Python magic creates this nice little table. And if I run it, I come up with something like this. Doing this on the entire graph, well, on top of this entire large cluster, these centrality scores are incredibly low. And that is another indication that maybe this graph is not fully connected and I should do other things. So let's talk about community detection. A component can be a community, but not every community is a component. So there's slight difference in them. In this case, we're going to run Louvain. Louvain is a modularity-based community detection algorithm. I'm not a fan of modularity, but it works, and a lot of people like it. It's incredibly fast. I run Louvain. I get a modularity score 7.4, so it's very high. And I can see that there's a number of communities in here. The highest one basically has, 309,000 vertices in it. Again, comparing against Network X, 865 milliseconds versus, well, 7+ minutes. So Louvain is incredibly fast. Diving into the biggest component, I can now run my centrality scores against these various components to see how they score. And you can see that a lot of the centralities score the same, but you can also see slight differences. I can see the different components, how each person, there's a different person in there. We are working on an overlapping community detection algorithm because it'd be interesting to see who are the people that connect these various communities together. I know that they're connected because they're all in one component, but who are the people that link them together? And it's interesting to see, I can just step through every community here and see who's important, how they're important. I could have also just run community detection from the start. Just said, well, I have my graph, let me just run Louvain. I would recommend that you don't start with that unless you really know what your data is. Now that I know that there's all these little components out there, I can run Louvain and get the same answer. But a lot of times I talk to people, I'm like, well, what does your data look like? And they're like, well, I have 7 million edges, and that's all I know. Knowing that there's lots of these small components can help drive what you do. Again, comparing against Network X, the fact that there's so many components, so many little components really doesn't affect the timing that much. cuGraph Louvain is still, sub-second versus, a little over 8 minutes. I think I can run the entire notebook in, just a few seconds. So the amount of time it takes to load the data and run Louvain in Network X, all of this notebook would have been done. And then just for fun, I started playing around with Jaccard. Jaccard is a similarity score. So who interacts, who behaves the same as someone else in the network? I ran Jaccard, and it's coming up with some people that are identical to themselves, which makes sense. But then I started running it down on other groups just to see, I created a simple algorithm where I can just specify a name of somebody in the Twitter data set and seeing how similar they are to some other people. So Trump was always popular during COVID time. But you can see that his similarity scores are incredibly low. So no one else in this cluster behaved the same as he did. So also, the overlap similarity is great when your set sizes are not the same. Jaccard is great if you're matching two sets. But if you're not sure of the set sizes, sometimes it will give you misleading data. So in this case, the top score, Trump and Brian Karam. So this probably means that this one person was always retweeting them. And that his set of tweets is really just a subset of someone else's. I'm getting the flag that I'm out of time, so. Go out to the cuGraph repo. If you like it, give us a star there. Feel free to contribute, participate in our discussions. All the notebooks are out there. Let me know what you think. With that, I will open it up for questions.
Okay, what questions do we have? Yeah, I'll come back. If you could type your questions into the Slack channel, that would be helpful.
Hi, thank you. Great talk. Sorry, I don't listen to myself on a mic too much. So does cuGraph do minimal cut sets as well? Minimal cut sets? Like what is the smallest number of cuts that you need to do in order to be able to separate the graph, basically?
So minimum cuts is on our roadmap. And if you go to the cuGraph page where it lists all the algorithms, you'll see that it is pending. We don't have it yet, but yeah, we do want to do minimum cut. max flow type algorithms.
Oh, thank you. And one more question about betweenness centrality. So when you calculate the approximate betweenness centrality, do you consider the approximation per island, or do you do it for the entire data set, ignoring that there could be multiple islands? And we know that there'll be so there are more than one connected component as such.
So for degree centrality, there is both a normalized and non-normalized value. And I believe if you normalize it, it does take that into consideration, but I will have to double check. I mean, unnormalized, you get very strange answers.
Okay. What other questions are there?
I asked this on the Slack too, but I guess I'll just, since I have the microphone, I'll just ask it now. Do you expect a similar performance speed up with non-social networks? So like ones that don't, have the same degree distribution that you typically expect with social networks?
So, I mean, social networks have this, power law or, just real blank on that, but they do have a degree distribution, and a lot of other graphs follow that. Mm-hmm. But a lot of times in real customer data, it's heavily skewed because it's, just a portion of what the whole world looks like. But we do see good speed ups even on more dense type networks. Within our back end, it is organized where we break data into hypersparse and just regular sparse. So CSR and DCSR. So if it's all hypersparse, we have special structures for that. Okay. So we do get good speed up. And we also don't waste a lot of memory by putting it into a DCSR structure.
Sure. Okay, cool. Yeah, thank you.
But you can always give me a graph that will break everything.
Hi, I was just kind of interested. We have some graph algorithms that probably not as well known, and is there a way to either contribute or propose to get it onto your roadmap? What's the best way to?
What's the best way to propose obscure algorithms? Is that what the question?
I wouldn't say they're obscure, but I don't see them on your list.
The easiest way is if you go into GitHub, just post a question and we can start a discussion about them.
Okay.
I have a list of probably 2 or 3 dozen algorithms that are on the backlog. Things like influence maximization, lots of other clustering algorithms. Max flow is one that's really important. A whole set of various data generators. We have RMAT, but we also want to do like LFR and things like that. So if there's an algorithm that you're interested in, jump onto our GitHub page, post a question as an issue, and I'll answer it and let you know.